Hi, I'm Zhang from Institute of Computing Technology, Chinese Academy of Sciences. I will introduce our recent work, DRack, a CXL-Disaggregated rack architecture to boost inter-rack communication. Today's data centers organize hosts in racks. Within a rack, tens of hosts connected via a top-of-rack or ToR switch, and each ToR switch is further linked to the network core. With the increased volume of processed data, data-intensive applications running in these clouds tend to scale their job out across more and more racks for acceleration. Therefore, a large volume of across-rack traffic is inevitable. We conducted an analysis of a public dataset from Facebook. It is a packet-level traces gathered from both Hadoop and front-end clusters over 1 day. We found that over an average of 85% of these two applications' traffic is directed to hosts located in different racks. Thereby, there exists a significant demand for inter-rack communication. This observation can be attributed to the following factors: job placement, resource fragmentation, and the requirement of large-scale applications. However, current ToR-based rack architecture faces three challenges in terms of inter-rack communication efficiency. First of all, data-intensive applications are increasingly leveraging advanced computing units, such as GPU, TPU, and FPGA for acceleration. This method significantly reduces computation time and generates data at a rate of gigabytes per second. It is several orders of magnitude higher than NIC's bandwidth. Second, the inter-rack traffic flow will traverse the oversubscribed uplink of the ToR, which will compete with other flows from other hosts. And at the receiving side, the many-to-one across-rack traffic throughput will be limited by a single NIC. To alleviate these challenges, we analyzed the dataset from Facebook. We observed that the bandwidth utilization of existing NICs within a rack remains low. That is, over 90% of hosts are not sending or receiving packets in 1 second for both Hadoop and front-end clusters. Besides, we conducted real experiments with data-intensive applications over 8 servers to find out the reasons. Firstly, an intuitive reason is that if a job can be placed on a single host, we call it a non-distributed job. The NIC of that host remains underutilized. For distributed job, each host computation time is different, which leads to hosts communicating at different times. Besides, the distribution of data between hosts can be uneven, causing certain NICs to processing a disproportionate amount of data compared to others. Driven by the implication of large inter-rack traffic demand and the underutilized NICs within a rack, we propose a new rack architectural concept, disaggregated rack, or DRack. It disaggregates NICs and memory from hosts and aggregates them as NIC pool and memory pool. For the NIC pool, it is shared by any host to transfer its inter-rack traffic, and each NIC exposes one virtual NIC or VNIC to each host. However, when transmitting data using all NICs, NIC pool's bandwidth can exceed the bandwidth of the PCIe link at a host or the total memory bandwidth of its local memory. The Compute Express Link, or CXL, enable memory and device pooling, which is a great fit for realizing DRack's shared distributed memory pool. The memory pool provides an aggregate read-write bandwidth exceeding the capacity of the NIC pool. DRack will introduce 4 benefits during inter-rack communication. In the computation stage, memory pool provides high read-write bandwidth to store generated intermediate data. Then the host can control multiple NICs to send packets concurrently, thereby mitigating the gap between the hardware computing throughput and the local NIC's egress capacity. DRack shift NICs and other topology components like ToR switches and aggregated switches up 1 tier compared to original ToR-based architecture. By appropriately varying between racks, DRack achieve a fully bisectional bandwidth between any pair of racks. Data is received by the NIC pool of the destined rack and DMA to all host memory device to fully exploit the NIC pool's bandwidth. Notably, DRack is not only orthogonal to existing job scheduling and placement strategies, but also unleashes their performance gains. For more information, please check the section 2.4. To build DRack, we need to tackle 2 main challenges. Firstly, hosts accessing to remote memory devices within the memory pool with CXL load store exhibits at least 2.7 times longer latency than accessing local memory of the same host. Secondly, mainstream data center applications are built on the socket and RDMA verb programming models, which rely on the TCP/IP and RDMA stack for communication. Therefore, the second challenge is how to modify these stacks to use NIC pool and maintain transparency to applications. To tackle the challenge 1, we leverage the memory interleave property supported by the CXL. The memory pool is separated into several interleave sites. IS0 is composed by a part of all host local memory and possible remote memory devices. For host I, the remained local memory becomes another interleave site, ISI. In this way, IS0 provides high read-write bandwidth and ISI provides low latency. Accordingly, we tailor the data placement policy. Network buffers or user buffers storing generated intermediate data are allocated in IS0. The data structures, such as descriptor queues that are frequently accessed by hosts, are allocated in ISI. To further hide the latency of accessing IS0, we integrated a DRAM cache within each host. To tackle the challenge 2, DRack enable applications use socket-based programming model. DRack employ MP-TCP to eventually distribute subflows between VNICs. We also implement a background kernel daemon to help apply and manage the memory pool. And a driver below TCP/IP stack acts as an indirection to orchestrate inter- and intra-rack communication. The protocol stack access network buffers, which are located at IS0, should go through the DRAM cache firstly. Then I will introduce how the DRack driver orchestrates inter- and intra-rack communication. For inter-DRack communication, DRack passes the reference to data instead of copying data across hosts. For each pair of hosts, there exists a unique reference queue. ID source stores the reference into the tail entry of ID dest reference queue. ID dest loads the head entry of reference queue, and it can access the data directly using reference. For inter-rack DRack communication, a VNIC typically has a pair of RX and TX virtual descriptor queues denoted as word queue. ID source store descriptors to TX word queue and ring USENIX doorbell via MMIO. Then USENIX read descriptors and TX buffers using DMA. At the receiving side, each USENIX DMA writes the payload to the RX buffers specified by the descriptors in the RX word queue. Finally, ID dist is interrupted by the USENIX and its protocol stack load store RX buffers. Given the lack of commercial products supporting CXL version 3 protocol, previous works evaluate designs using either software simulator or FPGA. However, considering DRack simulation requirements, current methods have drawbacks like low simulation speed or lacking flexibility. Therefore, we built a software-hardware co-simulation prototype. We utilize MP-SoC IPG to realize CXL-like protocols for resource pooling and running real applications. We use software simulator for flexible configuration of NIC pool, CXL interconnections, and inter-rack network topology. The prototype uses 8 MP-SoC IPG to simulate 8 hosts. For each MP-SoC IPG, there is a quad-core ARM CPU that can run real-world applications fast. MP-SoC exports the CPU load store instructions to IPG logic via HP and HPC ports, so that we can implement CXL-related IPs. In our case, they are DRAM cache, CXL-like protocol, and delay models. For software simulator, we implement it based on DeepDK, running on a commercial server. It mainly provides 3 functions: routing CXL MEM fleets among IPGs, routing CXL I/O fleets between IPG and NICs, and routing Ethernet packets among NICs. To validate DRack performance gain, we focus on accurately replicating the ratio of local and remote memory access latency on real hardware platform, according to the theoretical latency specified in CXL standard and the JDAC memory controller standard. Accessing the remote memory through a CXL switch is expected to add 170 to 270 nanoseconds to the local memory latency. We configure memory pool with maximum latency to illustrate the minimal performance gain achieved by DRack. To reflect performance gain under different NICs bandwidths, we varied NICs bandwidth configurations in experiments. We compare DRack with ToR-based rack using 2 types of real-world applications. First type is throughput-sensitive application. These 3 applications all present uneven utilization rates of NICs caused by application semantics. For example, in model training, we train a DNN and a large language model with ring-based or reduce and parameter server methods respectively. For or reduce, each host sends its gradient to its right neighbor, while receiving other gradients from its left neighbor. For parameter server, workers and parameter servers send and receive gradients in an interleaved manner. Therefore, no methods can fully utilize the NICs during communication phase in ToR-based racks. Finally, DRack reduced the communication time by an average of 37.4%. The second type is latency-sensitive applications, such as KV store and querying embedding tables in deep learning recommendation model inference. The existence of hotkeys leads to uneven traffic load at each NIC. DRack reduced the latency by an average of 33.3%. Besides, we conducted various experiments on DRack, such as integrating DRack with job schedulers, performance breakdown, and macro benchmark. For more information, please read the paper. Finally, what are the main contributions of DRack? DRack aims to deal with the problem that existing ToR-based racks fail to provide high inter-rack network bandwidth. Based on the findings that NIC's utilization rate is low, DRack proposed NIC pool and memory pool to provide aggregated inter-rack bandwidth for hosts. For evaluation, we built a CodeRack 8 MPI software IPJ-based prototype and validated its performance with both macro benchmarks and real-world applications. Thanks for listening. Please contact me or corresponding author Ke Liu through the following emails for any questions.